balancing of redox reactions. So in balancing redox reactions, there are steps that are followed carefully. Now, every redox reactions ought to be balanced just as it is in normal acid and base reactions or reactions between acids and metals to give a salt and liberate hydrogen gas. So just as other normal inorganic reactions ought to be balanced, so too are the redox reactions. If they are to make sense, all redox reactions ought to be balanced. Now, redox reactions can be balanced either in acidic or in basic mediums. And to balance these redox reactions, the following steps should be followed carefully. Let us take a look at these steps now that are involved in balancing a given redox reaction. The first step is we ought to identify the oxidation and reduction half cells. Next is to write out these half cell reactions. After writing out the half cell reactions, we balance other atoms other than oxygen and hydrogen, other atoms that are not oxygen nor hydrogen. And then we go ahead to balance the oxygen atom by adding water. That is the appropriate quantity of water that will balance oxygen atom where it ought to be balanced. By balancing oxygen using water, it must imply that hydrogen must also be balanced. So we move ahead then to balance hydrogen by the addition of proton, that is hydrogen ion. And then we'll move ahead to balancing charges by adding electrons. After that, we make the number of electrons to become equal on both sides. And then we add up the half reactions, the half cell reactions. That is to say, the oxidation half cell and the reduction half cell will be summed up. And that gives us the steps for balancing a given redox reaction in an acidic medium. But if it is in a basic medium, then that leads us to the last step, which will be we now have to add the hydroxide ion or hydroxyl ion on both sides of the equation so that it can neutralize the effect of the hydrogen ion, that is protons, that has been added initially. So these are the steps that are involved in balancing a given redox reaction. So with this now, we shall proceed to looking at how a given redox reaction ought to be balanced. So let's take a look at example 1. The first example we have here is to balance the reaction between manganese 7 ion and iron 2 ion. So looking at that, we have manganese 7 ion, that is to say, we can have a reaction between KMnO4 and the salt of iron, that is iron 2, for example, iron 2 sulfate, to give us a manganese compound. And of course, as we can see from the equation, that the iron 2 ion has been oxidized. So we will just proceed to looking at how to balance the given redox reaction. So from the example there, we have it that that's the first example. So we have MnO4 minus plus iron 2, and that gives us Mn2 plus and our iron 3. So all are in aqueous solutions, in their aqueous solutions. Okay, so with that now, we have written out our equation. So having seen the equation, we only have to proceed now to looking at which of these is an oxidation half cell and which is the reduction half cell. So we have to identify our oxidation and reduction half cell reactions. So from the equation given to us, we can say for sure that iron 2 we can see has been oxidized to ion 3. So ion 2 has gone to ion 3, and therefore we can say this is oxidation. And that implies that manganese is the reduction half cell. So someone may ask, how do we really know which is oxidation and which is reduction? Because in this case, it is easy to know that ion 2 has gone to ion 3. A question may be asked, what if I don't know that ion 2 to ion 3 is oxidation? How do I know that the other species is reduction? How do I know? How can I say that it is reduction for real and it is not oxidation? Okay, so let's look at that. Looking at MnO4 minus going to Mn2 plus. How am I sure that this is really reduction? Let us just see how to confirm that. This is manganese 7, and it has been reduced to manganese 2. So we can see. The question someone may ask now is, how do I know is manganese 7? That is to say, how do I know manganese has oxidation number of 7? How am I sure? To be sure about that is to remember that we have calculated oxidation number, how to get oxidation number. So this is MnO4 minus, and to know the oxidation state of manganese in this radical is to equate everything to -1, because it has a charge of -1. So you can see that. I believe you can remember that. So with this, we all recall that oxygen has oxidation number of -2. Oxygen has itself has oxidation number of -2. So this oxygen there has oxidation of -2. Apart from this -1 here, this -1 is for the whole atoms here, and that is why it is referred to as a radical. So it's for all of them, and we have equated it here, -1. But oxygen itself has oxidation state of -2. So it means that since I'm trying to look for the oxidation state of manganese, I'm still going to bring down my manganese. Then I'll say plus, what is the oxidation state of oxygen? Oxygen is -2, which means this 4 will multiply -2 to now become -8 equals to -1. So this is going to be manganese plus times minus will give us -8 equals to -1. And then to know my manganese, the oxidation state of manganese is going to be 8 go over the other side. This will be -1 plus 8. And -1 plus 8 is 7. So we can see that the oxidation state of manganese in this radical is 7. In MnO4 minus, the oxidation state of manganese there is 7. So we can see from the equation that manganese has gone to manganese 2 from manganese 7. So since manganese has gone from manganese 2 to manganese 7, it means it has been reduced. And since it has been reduced, automatically it means that the other species must be oxidized, or must be the oxidizing agent. So this is actually how to know which species is reduced and which species is oxidized. So we have identified that manganese 7 ion to manganese 2 ion is the reduction half cell reaction, while ion 2 to ion 3 is the oxidation half cell reaction. So with this, we can now write out our reduction and oxidation half cells. So beginning from manganese, so we have our manganese O4 minus to manganese 2. Let's just erase that and make it better. So we are trying to make that better. And let's shift this a little. Okay, so we have manganese O4, that's manganese 7 to manganese 2 is our reduction half cell reaction. So we simply write reduction. Why? Our ion 2 plus to ion 3 plus is the oxidation half cell reaction. So we have taken the second step. So we have seen step 1 and step 2. step 1, and step 2. So this is our step 2. Now our step 3. What is step 3? Step 3 says that we now have to balance other atoms that are not oxygen or hydrogen. Other atoms other than oxygen and hydrogen. So any other atom that is there that is not oxygen and that is not hydrogen will go ahead now to balance the atoms. So let us proceed. Now manganese O4 minus to manganese 2 plus. So we can see that the atom other than oxygen and hydrogen here is manganese itself. So is manganese balanced right and left? Yes, manganese is 1 at the left and is 1 at the right. So it means manganese is balanced. Now in the case of iron 2 to iron 3. The rule says, step 3 says we balance other atoms other than oxygen and hydrogen. We can see that this is iron at the left, iron at the right. And there is 1 iron left, 1 iron right. So it means it is balanced. So they literally are balanced. The other atoms other than oxygen and hydrogen are balanced. So step 3 has been observed. Now the next step is step 4. And step 4 says now we have to go ahead in balancing oxygen where it is needed. So in this case, we can see that the reduction half cell reaction is where we ought to balance oxygen, because oxygen is not found in the oxidation half cell. Oxygen is not found there, so we don't need oxygen from iron 2 to iron 3. But where oxygen is found is in the reduction half cell, and that is where we ought to balance oxygen. So we move ahead, MnO4 minus given to Mn2 plus. Now we can see that oxygen is 4 at the left hand side, but nothing at the right hand side. So we ought to balance oxygen by adding water, that is the quantity of water that we have these 4 oxygen atoms in it, so that it can balance with the ones at the left hand side. So it means we simply have to add 4 molecules of water. So adding 4 molecules of water implies we have added 4 atoms of oxygen at the right hand side, just as there are 4 atoms of oxygen at the left hand side. But that has created a problem. And the problem is, by adding 4 moles of water, or 4 molecules of water, it means we have added 8 atoms of hydrogen at the right hand side. So we can see that we have added 8 atoms of hydrogen. That is to say 4 times 2 for hydrogen is 8. But 4 times 1 for oxygen is 4. So it means oxygen is balanced right and left. But now hydrogen has been added at the right hand side. It means we have to add hydrogen at the left hand side too. But we are coming to that step. It is one step at a time. So we have balanced oxygen for the reduction half cell. The next is to go to the oxidation half cell. Iron 2 to iron 3. Iron 2 to iron 3. Do we need to balance oxygen here? No, it is not needed. So oxygen here is not needed. Oxygen isn't needed here. So we don't need to balance oxygen because oxygen is neither at the left nor at the right. So there is nothing like balancing oxygen at the oxidation half cell. So we simply have to move forward. We have seen step 4 now. So let's take a look at our next step, step 5.